Chris nicely showed me how to show off my example. I have a fairly long example of a nice sort of little algebraic simplifier, a little bigger one than before. It's not, of course, it doesn't have all sorts of things like transcendental functions and things like that. It also isn't very efficient. If I want to do this efficiently, and I do often, then I have to write special things for rational functions and for polynomials that are handled well and all that sort of stuff. But this is just an illustration of how to do it. And what you see here is the beginnings of the simplifier. I've got some stuff for sums over here which flatten them and other things like that. And a very similar thing for. That's interesting. The little red line means something. What does the little red line mean? Oh, it's spelling correct. How wonderful. That's
typical Mac thing.
But it goes back to do what I mean. Remember? Do him? Okay? Yes. Okay. So
doesn't understand scan.
Okay, good. So then I have products and things like that. I just want to show this off a little bit. Then there's the distributive lore, which is a little bit more careful here, because it allows stuff on either side of stuff. There's some numerical simplifications, nothing very exciting, collecting like terms down here, okay, collecting like factors to use exponentials. And then once you can do that, you can do a few examples, okay, and the examples are things like, well, the simplifying x times y plus x plus y plus 7xy plus x gives me y plus 2x plus 8xy. Right? It's the right thing. Okay? Or the product of xy and xy is x squared plus y squared plus 2xy, which is correct. Okay? Or x plus y times x minus y happens to put it in the other order than I would like, but it's x squared minus y squared. Okay? And so that's the sort of thing that's very easy to do and with this kind of simple technology. But the important thing I was talking about was not what this stuff was not. I would be very careful. I'm not trying to tell you about how to write term rewriting systems. Term rewriting systems are a whole art of their own. Okay? The important thing here is the idea of the combinators. That is, that I could build together, I avoid the syntax, I eat up the syntax of whatever it is I'm working with, turn this into little compiled procedures of the same shape that glue together and make bigger things of the same shape. And that's the moral of that story. Chris, okay. Your turn. Okay?
Here we go.
Oh, wait, I'll get rid of this.
Okay, is that working? Yes. Okay. So I'm going to look at something completely different, which is not going to talk about combinators, but hopefully tomorrow, if I have enough time and energy tonight, we will tie these together. Otherwise, we'll do something else tomorrow that'll be completely random. So I want to talk about using this language layering idea, and particularly the idea of using something like combinators, but not actually combinators, to build layers on things together in real cases. So I'm going to be describing programs that I've actually written that do useful things and show you that it can be done. And I'm also going to talk a little bit about what I call the holy grail of encoding, which is the thing that I once heard described as syntax-directed I/O, and I can't remember where I saw that. But in any case, so one of the things that I've done lots of is I've implemented a lot of standards. Okay, so things like HTML and XML and HTTP and IMAP and so on and so forth. And one of the things that's common about a lot of these standards is that they have, let's stay inside the lines. They have a lot of syntax. Okay, and that's not even thinking about stuff like programming languages, which also have lots of syntax. Okay, so the syntax is hairy, and in general you need something that will both read and write the syntax. And the syntax is almost always described, at least in RFCs, which is mostly what I've read, but I guess also in other kinds of documents. There's an extended BNF. Okay, so you want something like that to write your syntax descriptions in. You want to write them in a natural language, the language that is natural to the problem, which is not your programming language. Okay? You want some sort of a descriptive thing. But in practice, what ends up happening is that there's lots of parser technology, because the parsing thing is the hard part. But in general, the parsers are of varying quality, and stuff like output is almost never covered by the same technology. It's done ad hoc. You write a bunch of printf statements or something like that to generate your output. Okay? This is non-optimal. So, and also, the other thing is that basically what you end up with is a thing that's hard to work with, because if you look at the program, it's not always obvious how a simple change in the BNF, like let's say you go to a new version of XML or something, right? You need to make a little change somewhere. It's not always obvious how to translate that thing after you've totally forgotten what the program did in the first place. Okay, so the idea here is, let's see if we can do better. Let's see if we can get something that's closer to the BNF description, make it efficient, and ideally, but not in practice yet, although I'm working on it, make the output stuff do the same, or be driven from the same descriptions. Okay? So, and here's the Grail. So I was talking about. I've been working on this basically on and off for about 10 years now in various forms. And I'm going to tell you about a couple of the things I came up with. And if I get to the end, I will show you a partial success on reaching the Grail. Okay, so XML. At some point in the past, I decided that it would be nice to have XML support in MIT scheme. I was just fooling around at the time, and it turned out that it was actually quite useful. I'm not sure why, but it was. We used it for a lot of things, okay? And most importantly, I think, is for XHTML, it allows us to do a lot of web programming, okay? So I started by looking at the XML, trying to figure out how you would write a parser for it, and gave up very quickly and decided this was the wrong thing, right? What I wanted was some sort of a description language that I could use to write the XML parser as the BNF. Okay, and I actually started with something like one of these combinator languages that Jerry talked about, and I ended up abandoning it. I wrote the whole thing, and then I threw it away because it wasn't going to be anywhere near fast enough to do character parsing. Okay, so I rewrote it from scratch using a syntactic thing in a compiler and the whole thing took maybe a month to write. And in retrospect, I probably, now that this idea that we have of doing injection is actually a much nicer one, so I could have done this, but we hadn't thought up that idea yet. So it's a relatively recent development. So I still have to try that experiment. So I wrote this thing, and we ended up getting an XML parser out of it, and it works. It's not bad. It's not particularly good. So here's some examples, and I think it all fits on the screen, yes? Okay, so here's some examples of what works well. Okay, so you could write things like the start tag and the end tag and the content. And these are the actual, for XML 1.0, those are the actual rule numbers from the standard. So I just clipped these right out of the code. And you can sort of see that this is kind of straightforward, right? I mean, you have a start tag, this bracket thing you have to understand, which is basically saying that there's a bracketed thing which has two ends, and then there's the middle. And the ends are the first two arguments, and then the middle is the rest of it. Okay? And so the beginning is this, the left bracket with a bunch of stuff, and then that's the end, and then you have an attribute list in the middle. And I'm not going to show you all the stuff. There's many, many, many rules. But just to give you a feel for how you would write something like this. And here's a simpler one, where this is, again, a different name for no good reason, for the end tag. And the content is basically just you're doing sequences of and alternatives, and this star is the clean star, and it looks like BNF. Okay, so that's the good part. Now, here is the top level thing is not so good. Okay, here we had to actually write the parser using Scheme, and mostly this had to do with the namespace processing. Before I put in namespace processing for XML, it worked pretty well, but like the namespace itself, fixing this required breaking the model and all that stuff. XML namespaces, well, they're a great idea. They really have a crappy implementation. So This is not so good. It's not terrible, but it's not, I mean, this is all scheme code. There's no abbreviations here. There's nothing to help you see what the program is doing. It's complicated. And then, even worse, I don't even remember what this does. I mean, there's somewhere up here, there's a content that's being done. And there's the end tag being parsed there. Then there's all this error checking, and don't ask me. I don't know. I don't remember what it does anymore. It's a mess. So this is not a completely successful experiment. What we did was we got a useful object out of it. But the most important thing was that we got a useful, oh, and here's the other part, sorry. And here's the output, of course, has nothing to do with the input. It's a completely different program. Okay? And the output's not too hard to understand, but it would be nice if it was just automatically generated from the BNF, and it's not. So the good part is that we got a parser language out of this that is close to BNF. It allows you to do all kinds of cool things. So basically, you can write these BNF formulas, and then you can do transformations on the things that are being parsed, arbitrary transformations, so that you can basically accumulate data incrementally, and then at the end of the day, after you've parsed some entire thing, you have very compound data structure that you defined in the rules. Okay, that's a good thing. Now, and then the other thing is that the pattern matchers. So, okay, the pattern that you write, that is a BNF pattern here, turns into a standard procedure. So it in effect is a combinator of the kind we've been talking about here. It has a single input, which is the stream that it's using to parse from. Okay, it's a special stream. It's one that's buffered so that you can back up in it because you have to do backtracking. And it has a single output, which is the stream of values that the parser produces. Okay. And the nice thing about that, besides the fact that it allows you to mix and match them very easily, is that you can also just write standard procedures and plug them in as if you had written patterns, which is what we exploited to do the ugly stuff here. Okay. So even though the language is not completely successful at doing the XML parsing, we're able to bend it enough to make it fit. So it's sort of, there's a lesson here, basically, which is that you shouldn't imagine that you're going to do really useful work in one of these languages without having escapes. You really have to have a way to get out of your model because the real world specs are almost always more complicated than the neat little models that you want to make to capture the bulk of them. Right? I don't think this is unusual to anybody here, right? There's 80% of the work is easy and it makes sense. And then there's that other 20% that people weren't thinking clearly or no one understands it or whatever, but you have to be able to get around that crufty stuff to get a good result. Okay? So that was one of the nice things. The other nice thing, let me see if I think I have some other examples here. Yeah, so here is just a brief description of some of the components of the language, just to give you an idea of how it might work. So there's a separate matching language that allows you to match groups of characters as a whole. That sort of looks like this, but all it does is match. It says, okay, I want you describe some pattern that looks like an eBNF pattern. It matches the whole thing as a unit, and then it returns that string as the value for the parser, okay? And then you can group these things together in sequential form as alternatives and repeats. And there's, of course, the standard things of repeats where you have to have a minimum of one, you can have limits on the repeats and all that stuff. But more interesting here is the transformation architecture. Okay, so what you have is a pattern that matches something, and then you have, so if the pattern, so there are several of them. I'll do the more general one here first. So when this pattern matches something, it produces a stream of results. Transform basically says, okay, here's an expression that gets evaluated by the evaluator. It's a scheme expression that produces a procedure. The procedure takes the stream of results and tweaks it. Okay, it can fail. It can change the number of results. It can just package them differently, throw some of them away. Doesn't matter. It can do anything it likes to the results to transform them into some other set of results. Okay, and this is the hammer basically. This is the one that the most general part of what this thing does. But more usefully, there's this thing called encapsulate, which is a restricted version of transform that says, give me the string of results. I'm going to do something special with them, like put them in a data structure, and I'll return you one result, and that should be the stream for the entire thing will be just the one result. Okay? And then there's a thing called map, which basically does a per result, basically a per element map of this procedure across the results that come from the pattern. Okay, which is useful if you have multiple results coming out and you want to do the same thing to all of them. So this is, as it stands, this is not a bad collection of things. And there's other stuff with it, but basically this is a way of capturing BNF and also having the ability to escape out into scheme when you want, into the underlying language, but you can still capture a lot of useful behavior that way. And so I guess what I think the thing that I want to emphasize here is that, first of all, because the patterns turn into scheme procedures, you can get into the pattern language easily. And things like the transformation architecture, and there's another hook that you can use to actually just break out into scheme altogether, you can switch between the languages very easily. So it integrates well, even though the result may not be that pretty. So here's a different example of something that we actually use. Here's a bit of an ISO 8601 parser that gets used in particular, well, for all kinds of things, actually. So some of this stuff ends up looking pretty good, okay? So here we have basically you have something that parses a date time, and in ISO 8601, maybe I should write an example just so for people who aren't familiar with it, you have something that looks usually like a bunch of years, month, day, followed by T, followed by hours, minutes, and seconds, and then a time zone that's optional. Okay?
Yeah. What did you say what alt does?
I'm going to. Well, I said it's alternatives, and I will get to that. Okay? So, for example, today is 2009. Oops. 01. What is it? The 13th?
Yes.
T, and the time is 15:25 roughly. 15:25. Let's say 00. Okay, and we're at minus 07, 8, 8:00. I haven't quite adjusted to being in California yet. I would have known it was 5 for the East Coast. Okay, so what happens here is that we're going to basically have the parts of this thing. So we have a date, we have this T, then we have time, and a time zone. So there's 3 parts, and they're sequentially in here. There's the separator. And so the seq says they're in sequential. And then there is this funny thing going on, which is alternatives. And this has to do with the fact that ISO 8601 defines a basic format and an extended format, and I can't remember which is which. One of them has the things like the hyphens and the colons, and the other one doesn't. Okay? Go figure. So strictly speaking, you either choose all basic or all extended, but it turns out that for various reasons we needed to mix them, and I think the comment actually explains it, but whatever. So this basically just says any mix of those will be accepted by the parser. Okay, so this is yet another example of Jerry's rule, make your program broader than it has to be. This will certainly accept all valid ISO 8601 dates with some restrictions. It'll accept some stuff that isn't actually valid too, okay, but whatever. So, and here's the basic date thing, and of course, again, there's 3 different date formats. Okay, we have a date format, which is the standard one that I just showed you, which is year, month, and day. And then there are ordinal weeks and ordinal days. Okay, right? So you can basically have a thing that's a year, a week number, and then the day of the week, or a year and an ordinal day. Okay, and those can be parsed the same sort of way, and they just get transformed by this transform statement into the standard format, which is, and then used that way. Okay? So this actually does a reasonably good job of capturing that structure. Okay, it's straightforward. So there are cases where it actually works pretty well. Here's a case where it doesn't work quite so well. Okay, we have to parse the actual numbers in this, it turns out that it's a pain because there are restrictions on how many digits you can have and stuff like that. So it turns out it's easier to just write scheme code to do number parsing and tell it the details, like, okay, years can have to be between 1582 and 10,000, right? For whatever reason. Months, okay, there are limits, number of digits they have to have, the limits on the number of digits, so on and so forth. It's very easy to write this in scheme. Big, but easy. Writing it in patterns is clumsy and wouldn't be less obvious. Okay? So that's an example. Google, by the way, does this sort of thing already. Okay, I don't know how many of you are familiar, but Google has. I found out about 2 months ago that Google has got a combinator-based parser language in Google's source tree, which you can go look up and see for yourself. But basically, it's very much like the matcher language that Jerry was talking about, but it's a different set of combinators, but it really is a combinator language. Okay, and maybe one of these days, if I have some time, I may figure out how to compile that stuff, okay, using this nice trick. But I just found out about it, and I'm a little busy. So, about a year ago, a little before I left to come here, for no particularly good reason, was writing a thing to support HTTP. Okay, and I needed to parse HTTP headers. And of course, my first thought was, I have this language, let's just use that. And it turned out, well, it didn't work too well. It turned out that it wasn't quite the right fit. So I took the opportunity to say, let's try and let's do it again and try something different. Okay? And the main thing, can I say this? Yes, okay. So the main thing which got me started in this is that HTTP, most of the header definitions in HTTP use a shared tokenization structure. Okay, now it's much easier to match streams of tokens than streams of characters, because you've already done some of the parsing to begin with. It's just simpler to describe the stuff. But the matcher that I'd already written didn't know how to deal with that stuff. It could only deal with streams of characters. Okay, so I decided to make a new one with some different characteristics. Okay, so first of all, in the previous one, there are discrete. So when you return results from a parser, you get a vector of things, okay, using a concrete type to describe the result. Okay, this has some drawbacks, mostly that there's a lot of vector copying going on in the background when you're gluing stuff together. Okay, so the first thing I did was I said, let's not use concrete types there. We'll use an abstract type, and then we can tweak the algorithms in the background to make them run faster. Okay, that was the first thing. The other thing was the compiler for the character-based language was very hard to read. It was exceedingly clever, if I do say so myself, but so clever that I couldn't remember how it worked. So I tried to write a simpler one that I could remember when I looked at it again, and I think I succeeded. I don't remember if I have any slides of the actual compiler code, but in any case. So, and then the other thing was this succeed-fail continuation, which Jerry was talking about, a succeed return sharp F. But it turns out that it's actually simpler to think about these things if you have two continuations and you never use the return value for anything. Okay, so what ends up happening is that you in effect write combinators that look like, you have some inputs that are standard, and at the end you put what I like to call win and lose, mostly because they're shorter. Okay, and well, win is shorter than succeed anyway. And when you win, you pass. I see, I'm just getting too close to the whiteboard and it's had trouble. You win, you give it some stuff, and you also pass along the failure continuation. And when you lose, you just call the failure continuation, okay? And hopefully, I'm not sure you guys over there can see that, but if anyone doesn't understand, just speak up, okay? There we go. Magic board. Okay, so it turns out that basically, at least once you internalize the idea of continuations, of using this continuation passing style and scheme, it's much easier to think about this than to think about the mixed style. Because at any given moment, right, I mean, you've got the control in your hand, you just keep going forward, and you never return. You just keep going forward, okay? And it's relatively easy to think about, but you have to make that jump. It's a difficult jump if you've been doing stack-based architectures all your life. And we'll get back to that later when we start talking about expression, getting away from expression constraints, because that, in fact, is a problem for other kinds of things. Okay, what else do I have here? Use patterns that correspond to constructive. I don't even remember what that means anymore. Crap. All right. I did. I wrote it. Well, actually, some of it I wrote this morning, and I just don't remember anymore. Okay, functional source. Okay, so in the original character parser, I used a side effecty stream on the input. So basically, you would pull characters out of it, and if you wanted to backtrack, you had to save a pointer before you started, and then you would go back to that place. Okay, and it turns out that, as you might imagine, if the stream is some sort of functional thing, it's easier to work with. You don't have to do the side effects. You just hold on to the head where you needed it, and then you just pass it along. Okay, so there's no, it simplifies the code quite a bit, and it's easier to think about, which is more important. So, not the right place, but, so, okay, so here are some procedures for defining things. I'm not going to go into them in any detail, but basically, so you want to define a thing that knows how to deal with one particular HTTP header. Okay, so it knows how to parse it, and it knows how to write it out, and just for fun, there's a little thing in the middle that knows how to test a particular data structure to see if it's one in the right form for this header. So that if you, let's say you want to decide you're going to deal with your headers by manually building up the data structures and then passing them into something, you can use this to test to make sure that the structure you built is consistent with the model for that header. And I'll show you an example of that in a minute. Okay, and then these other things are basically just, these are cute little things to deal with. HTTP's comma lists, comma separated lists, which are ubiquitous. So there are a lot of them, and there are a lot of variants on them, and lots of these headers just have to have the same pattern. So here is the comma list. I'm not going to go into detail. If you've ever seen it before, you know it is ugly. It is disgusting. Comma lists in HTTP, you can put the commas anywhere. Okay? You can have arbitrary sequences of commas in one of these comma-separated lists. And the only ones that matter are the commas that are in between stuff that isn't commas. Okay? So you can put 100 commas at the very beginning, and it's as if you didn't put anything there. But if you put, and you can put 3 in the middle, and it counts the same as 1. So go figure. It was a pain in the ass to program it. Okay? So here is a specific example. So except encoding, let's see if I can remember what one looks like. So except encoding accepts, what do encodings look like actually? This is not transfer encodings, so this is going to be the character encodings, right? gzip? That's not a transfer encoding? Okay. No, that's the other, right. Okay, so it's gzip or something like that. So I probably should have chosen except charset, which is the same thing. But except encoding, you have things like gzip, and you can have compress, and identity, I think, is one of them. And then these things can have little parameters stuck on them, the most typical one being q equals and some number. Q equals 1, Q equals 0.5, etc. Okay? Q equals 0.1, and then those are all separated with commas. Okay? And then, of course, in addition to this Q parameter, you're going to have arbitrary numbers of parameters besides that, both before and after the Q. But it turns out they mean different things if there's a Q there or not. You can't just put the Qs anywhere you like. They have to be in a specific place, and don't ask. Okay, so here was an example. So this is a tokenized parser. So we're using this comma list plus, meaning that it has to have at least one thing, and it's comma list separated, and that we have a standard way of parsing these things, which basically here's the parsing the name, the token, and then the semicolon followed by a Q parameter. Okay, so this one actually doesn't take other things. No, this only takes one Q param. Okay, so that's good. And then a list. Make a list of those things. And to write them out, there's a special thing that writes them out with semicolon separating the parameters from the value. And then there's a predicate that knows how to parse the data structure that this thing talks. Okay? So this isn't too bad, especially since these procedures here are shared by about 10 or 20 different headers. Okay, so you write them once, and then you write a bunch of different header definitions, and all those header definitions look roughly like this. Okay? So that's not too bad. Now, there is a problem with HTTP is that there are headers that don't use the same tokenization. Okay, so for example, you can put in I think the standard one that I would think of is the host header. All right, host takes a thing like localhost :8000, let's say. Okay, and I don't remember if there's anything else in there, but at least. And this thing does not use HTTP tokenization. It uses the BNF from, if I remember right, it comes out of the URL spec, the URI spec, okay? But it's from some other spec altogether. And they say so in the spec. You have to go look at that one. It has a different tokenization, it has different, so you can't use the tokenizer for this. I don't even know if it would work. It might, but it's not the same language. And there's some other ones like email addresses that have to be a whole different parser of their own. Okay, so you can see this gets really fun really fast. So we want to have have two different ways of dealing with things. We have a tokenized version, and we have a non-tokenized version. Okay, and the only difference really here is that the tokenized one is going to use a tokenization process called string arrow tokens, and then it's going to pass that to a parser that is a structure parser, and the structure parser will do its thing. Okay, and here's an example this is the abstract result syntax, basically. That's a procedure that will access that abstract structure and produce a value. There are a handful of those things for manipulating the abstract results. And the direct parser basically uses the old parser, the character-based parser, because it was there and it was easy to use, and I didn't care, quite honestly. And you can see that I use a concrete result here. There's a concrete structure coming out of that. Okay, and that's the top level of the tokenizer, not really worth going into. And yet again, here's a new language that I wrote, which took a couple of hours. Write a state machine language to write the tokenizer, because tokenizers are very well captured by state machines. Okay, so the state machine language basically says each one of these things is a state. The leftmost thing in each one of these is a transition test of some kind. So you have a test for end of file, or basically end of the character stream. You have character sets or characters for various other transitions. And then you have something, a catch-all for the end. And the end of this list is basically the new state, and anything in between them is something that you do before you do the transition. Okay? So the very first one, basically, you have the only one so you have a saved character here. So if you start something that's a token, you're going to push a character, and then you're going to move to in token, which does not appear here. And if it's a separator, then you spit out the character as a unit, because that will be a token of its own. And then you move back to tokenize the main loop. Okay? And the other ones are pretty much the same. There's a lot of details here. Okay, and there's about 3 more of these And then there's another one written in Scheme that turned out to be easier to write that way than to put in this language. Again, okay. So, and here are some examples of direct parsing, and one that's actually really interesting. So the host one I told you about, and it's got this direct parser. I'm not going to show you the parser, it's just a random thing. And here's another one. And then finally, the HTTP date, by the way, uses that ISO stuff that I was talking about in addition to 2 other formats, both of which are effectively obsolete now. And then there's this one, if range. Well, if range is funny because it can be tokenized for some forms of it and not for others. So you have to be able to handle some mix, okay? And the reason I put this up here is that you have, here's a really good example of why these languages can't ever really work properly, right? I mean, you have the spec explicitly says that it has to be like this, right? I mean, it says, you know, yes, there's a form in which it is a standard header, and there's another form in which is a random header that has nothing to do with it. So, you know, you have to be able to deal with these, you know, the guys who write these specs, and they're random. You know, and I think Berners-Lee was probably responsible for this, and he's about as random as anyone I know. So he's a really nice guy, but random. Okay, and we're almost done here. Okay, so that's all I wanted to say about that. And I have one more slide in which I have a partial success of actually building something that uses what I consider the right model. So here is a part of an assembler disassembler, one instruction definition. Okay, and what this thing does, this is for a virtual machine, and I believe that these underscores here are the same as what Jerry was using question mark for. I wrote this about 2 years ago. I've forgotten now. And basically, so there's a, you know, this is means it's a variable. It's the name of the variable, and then there's some sort of a predicate here that is a qualifier for that particular binding. And this generates both the assembly fragment and the disassembly fragment. Okay, so this is what I want to be able to do for all kinds of things. I want to be able to describe the syntax, and I want to have the codec, basically the coder and the decoder generated from that. I don't want to have to write them by hand, okay? And I think this is possible, but I haven't yet succeeded in doing it in a more general way. Carl?
This has been done before. The New Jersey Machine Code Toolkit will take an instruction description that you generate using yourself.
I believe it. I think this is an easier problem than the more general parsing issue, which is why I was able to do it here, but not in the other case. But I want to do it in the harder case. So, yeah. So this is basically, you know, yes, I've failed, but, you know, I have a minor success here, so you can't blame me for being completely clueless here. Okay? So this is a nice thing. But so this is basically, so hopefully you get a feel that you can use techniques like this to layer your languages and get some abstraction. So you can write descriptions at an appropriate level and yet still be able to deal with the real world. Okay, ugly as the real world can be. Okay, and that's all I have for today. Yes?
People there was a time when people made very pretty computers, like the PDP-6, PDP-10 system. And that was, DEC made this very beautiful computer where basically the machine language was a microcode almost, a horizontal microcode, and you could decode an instruction by looking at it. And I believe it was Gosper, but I'm not sure. Was it Gosper, do you remember, who made the opticoder for DDT? That was the dynamic debugging technique, which was basically both could encode and decode a symbolic instruction name like half left to right 0 immediate, okay, into the machine instruction or go the other way, and it took a very few locations, like about 150 machine language locations in a PDP-6, and it was written in DDT. At the top of DDT, I can't remember the place where it was, but it was generated by a macro, okay, by a macro that was only 12 lines long called barf. Anyway, maybe I can dig that up.
Okay.
We could get on to that.
Anyway, so let's finish a little early, but that's
Okay.
pretty much what I wanted to say here.
Yes.
Okay?